My name is Matt Fields. I've been involved with various schemes where we've used the technology following Silverstone and applied them to the network.
Hello, and I'm Adam Dean. I'm the technical manager that was the technical manager upon Silverstone and carried through into the highway sector on the A55. Matt speaks more around the technology and the paving, and I'll speak to you more about the technology and the materials that we used on the A55 when we took the Silverstone experience out into the network.
Tarmac are an industry leader in respect of deployment of paving technology within the UK. Since completion of the Silverstone circuit in 2019, we have been able to successfully utilise technology and best practice learned both on highways, network and within other specialist aspects. The benefits to the client are a marked improvement in quality and ultimately end user satisfaction. Here is a short video that gives insight into what is possible with the right approach.
For Silverstone, it really is important. So for us, it's really important.
This is the third Formula One track we've done, so we've obviously got a reputation for it.
That we produce the best scheme possible with the best results using the best resources.
When the construction crews and the material business come together, then it is an awesome operation to behold.
Silverstone needed a bespoke, very high performance surface to deal with the stresses given by Formula One cars.
Everything needed to be integrated into one team. We analysed where our weaknesses were and where our challenges were, and we planned around them.
The aggregate from Bayston has been specially chosen for its unique and specific quality.
By us washing the dust, it allows the mix designers to get the correct consistencies for the Silverstone racetrack to make sure that we've got the right materials in the right places at the right time.
So the key consideration is the very high shear forces exerted on the asphalt by Formula One cars, particularly under braking. They can exert enough force to create ripples in the asphalt.
Indirect tensile strength, stiffness and binder adhesion allowed us to determine the durability of the mix design. Surface friction testing was carried out in situ to ensure that the resulting material met the friction requirements for the specification.
A lot of this project has been about ensuring consistency of the surface finish and using new technology to deliver really excellent results.
New bays were erected, cleaned to make sure there's no cross-contamination. Backup procedures are in place. Electricians are ready to be called out, fitters on hand. Once the asphalt has left the mixer box, the technical department can then inspect it, temperature check, and make sure it's all inspected.
Reprofiled the whole circuit from taking nothing off to 140 mil in places.
So we set up a bespoke traffic management system to minimise the amount of time that any truck spent getting through to the paving machine and reversing. Critical pressure points, other than the material specification and the parameters for the laying of that material, were for us not stopping. Once we'd started, we had to keep paving, and that's where we utilised BPO.
Being able to plan the logistics gave us a better control of getting the right rolling temperature and programming the lorries into the paving train from mix to lay.
So using BPO, we were able to look at the installation from both sides. So if we were able to produce faster, then we could lay quicker. Equally, if we weren't able to produce as fast, then we needed to lay slower. And to get that balance right can be quite hard, but using the software system, it was quick and simple.
That gave us then the ability to utilise the technology on the paving machines to get the smoothest ride possible.
We had to get a tolerance of less than 2 mil on a 4 metre beam, which is more onerous than an airfield. The consistency of the material was impeccable.
Every single truck was laid, there was no wastage.
We've done a lot of preparation, it's a prestige job.
Now we've experienced the technology that we've used on here, it would be nice to push that forward. It is the future.
I'm really keen that we use some of the knowledge that we've gained here and take that forward into our day-to-day business.
Because the grip level's there, we've got increased speeds, lap records have already been broken on the circuit, and it actually makes it a lot safer as well.
For me, it's that British excellence, start to finish. It's being proud to be British and to be able to do it and stand here and say, we're moving Britain forward with our technology.
The video demonstrates what is possible when the correct planning and implementation are present. However, we realise that not all roads are or need to be racetracks. As a result, we have broken down the operation into its constituent elements that enable us to use only the technology that will generate the improvement that is required by the client. These start with machine control. This can be used for both milling and paving operations and is generally used when the level tolerance is critical. This allows the plant to work to a design model with minimum human interface for level control. Multiplex milling. This increases the number of level control points from the traditional single drum sensor to 3 by the addition of 2 further sensors placed at the front and rear of the milling machine. This results in the milled surface having a significant amount of level discrepancies removed by the planer prior to the placement of any surfacing. This can be used in conjunction with mill assist that controls both travel and drum speed of the planer to give an ideal finish for thinner overlays. In effect, it creates a fine mill finish that removes the risk of any undulation reflecting through to the surface course. As you can see from the graphic, the multiplex reduces any bumps that are present by a significant amount. Tarmac have several milling machines equipped with this technology, and it is a low-cost option to enhance the ride on any existing carriageway prior to surfacing. LiDAR. This is a laser scanning via a moving vehicle or freestanding station. The surface is scanned to millimetre precision, identifying any deviation or bumps to either design model or as a standalone scan. This then allows us to rectify any irregularities in the receiving foundation prior to placement of the next layer. Transfer vehicles, otherwise known as feeders within the industry. The main benefit is to remove contact between delivery vehicle and the paver that can result in bumps within the completed surface generated when contact is made. It allows for the paving train to lay with a continuous, uninterrupted flow of material. This greatly improves the smoothness of any surface placed by this method. Up to 35 tonne can be held within the paving train that further reduces the need to stop paving and allows for a constant paving speed without the need to adjust the tamper settings on the paver. Averaging beams. These operate in a similar way to the multiplex function of the milling operation. The sensors are increased to 3 from the standard 1 on a conventional paver. This allows for the paver to remove further irregularities within the surface by increasing the level control plane by up to 13 metres linearly. Used in conjunction with transfer vehicles, this gives the greatest improvement in surface regularity. Echelon paving. Linear joint failure is a major factor on highways, particularly in situations that subject a joint to repeated trafficking. By paving echelon, a more robust joint can be produced that mitigates early joint failure on heavily trafficked roads. Thermal imaging gives an immediate visual indication of any temperature variation in the paved mat and clarification that the correct rolling temperature for the material has been achieved. This can then be used to target the roller operation for compaction. Cold material is a major contributory factor when insufficient compaction has not been achieved. It can also remove the need to deploy a technician in high-risk areas with moving plant. BPO is a planning and logistical tool. It enables accurate haulage requirements to be calculated to ensure the desired paving speed can be met by considering radials from the asphalt plant and material flow rates. The live feed information allows for the paving train speed to be managed to ensure that a continual supply is generated. It has the benefit of being able to produce performance data that can be further used to improve efficiency. The system is also able to allow for haulage being utilised for return loads of planings from the site. We have recently deployed this technology on a number of contracts. They are Catesby Tunnel. ARP have been working to develop the tunnel as a vehicle test track for the past 8 years. The tunnel will be used for enclosed vehicle testing and offers a controlled environment of no wind and stable temperature. This allows the testing to be done in a very repeatable way, and therefore progress in drag, noise and cooling is far more achievable than normal track testing. The most important requirement is for a smooth surface. ARP have decided on an IRI, International Roughness Index, as a measurement of smoothness, and issued a target of less than 1 but as low as possible. A smooth runway will have an IRI of between 1 and 2, and a new motorway in the region of 2. As such, it was a difficult target considering the fact we were also operating within the confines of a tunnel. The initial trial has produced an IRI of under 0.4, that is close to the figure of 0.28 achieved at Silverstone. Myra have asked Tarmac to produce the flattest test area in the world within the facilities on this 300-metre circumference circle and central approach. Over 53,000 tonnes of material were laid in a 3-month period. Base and binder was laid using machine control, and the surface course laid in echelon using 2 gangs and averaging beams. The main objective was to achieve an IRI of less than 1 in a linear direction of paving and omnidirectionally. We achieved these objectives. Cavway Autonomous Vehicle Test Facility. This is a whole new test track being developed for autonomous vehicles. A requirement of the ADAS platforms within this test facility require a tolerance of plus or minus 2 mil. One of the most successful technology deployment schemes recently completed is the A55 in North Wales.
The reason we wanted to engage with Tarmac for this particular programme of works was we'd identified the need for a more durable overlay to the concrete carriageway on the A55 and A483.
The asphalt had come to the end of its design life. Our technical guys came up with a solution for using sami and multilayer to help distribute the strains caused by the joints in the concrete and prevent cracking in the final finished surface.
Well, the ECI stage really started around 2 years ago when we were preparing the design for phase 1 of the works from Broughton to Eulo, and Tarmac were extremely supportive in developing that design. The joints arrangements with using echelon paving was quite key to improving the surface quality and durability of the surfacing.
A55 is a very busy route. There aren't any easy diversion routes if you're closing the carriageway. We work together with Namutra, with Flintshire, with our own traffic management department. The final solution was closures at night and at weekends with lane closures during the day.
That was extremely important because of the need for support from local authorities to make use of their network to free up the road space we needed to undertake the works. That was really important part of the project. That phase of the works went particularly well. The coordination of the Tarmac teams and taking multiple construction activities was highly successful.
The reason we used the 3.8 metre planer was down to 2 factors. Firstly, production, and obviously with increased safety. In terms of the production, we set ourselves a very ambitious programme of completing 4,500 tonne to be planed out and relayed over 2 big weekends. The reason we used echelon paving and feeders on this scheme was so we could provide the client Namutra and Welsh Government with the best possible finish on the project.
The dual carriageway has no hard shoulder, so to get delivery vehicles in and out of the scheme is extremely difficult. The solution we came up with in the end was to work in the opposite direction to the way we would normally. We closed off the junction prior to where the work started, and that enabled safe egress and access into the site for all the delivery vehicles.
The echelon paving method we adopted on this project was a follow-on from the successful project that Tarmac completed in the summer of 2019 in Silverstone, The echelon paving method allows us to have a seamless pavement. It eliminates the construction of a longitudinal joint. The key point about using BPO echelon paving is it allows us to manage the flow of delivery wagons onto site. So the site team could keep an eye on where the delivery wagons were at any one point to ensure that the paver didn't stop during an operation.
Tarmac are on our current framework and they've been performing well. The relationships have been excellent. The overall surfacing design that eliminated the transverse joints that we had previously has improved the ride quality quite significantly. The tolerances that the technology you've used on your surfacing plant is quite noticeable in the overall ride.
We were delighted as Tarmac to have the opportunity to work with Minutra and Welsh Government on this prestigious project. From day one it felt like one team. The client was very forward thinking and the collaboration between both parties was excellent, and we just hope that we can continue our excellent working relationship with Minutra and Welsh Government in the future.
The scheme had many significant challenges to overcome. Tarmac had detailed discussions with the client to produce a design that addressed the issues that included width restrictions that generated the need to carry out the works utilising overnight and weekend closures, greatly reduced the impact on the travelling public. Some movement in the existing concrete slabs was identified following a detailed ground penetrating radar survey. This resulted in some slabs being replaced and others requiring grout injection for stabilisation. The height of the existing safety fence dictated that the design needed to mill into the existing concrete to facilitate the placement of a two-layer surfacing solution. This solution included the use of a sami layer to help offset the risk of reflective cracking that is common on most concrete roads. Both the sami layer and the surface course were laid in echelon with the use of transfer vehicles and averaging beams. The result of this application of working methods and technology generated a rolling straight-edge result of 8 over 4mm defects out of a permittable 398 within the 2.7 kilometre length. This scheme gives a good example of how bringing paving and material technologies together gives excellent results in performance.
Right, thanks Matt. So Matt's talked about the technology that we use in the paving train and the various bits of kit that we've used to achieve all these amazing results. I'm going to go on and talk about what we have to do from a technology point of view when looking at material selection. So there's a lot of technology as Matt's gone through, but equally we have to get the right materials to deliver these projects and get the benefits that we've seen. So when we look at materials, there's not much you can really do with a grading envelope and the other parameters we've got to work with. The clever bits come with the binders that we use in the bitumen. So in my section, I'm going to talk around bitumen technology and the use of polymers and how we've used these polymers to tailor make an asphalt solution for the A55. So as many of you know, asphalt tends to reside in 4 families, and there's only a limited amount of things we can do with aggregates and gradings. The biggest opportunity we have to make materials more aligned to your site-specific requirements is to look at the bitumen, modify the bitumen to give the performance. So in this schematic here, you can see there are various ways that we can modify bitumens. The one that's used more predominantly than others is SBS, which is styrene butadiene styrene. And in this case, this is the bitumen that we used, a polymer based bitumen from an SBS. As you can see from the picture, we managed to get from a polymer but 2 behaviours that are actually opposite to each other. We get rigidity and elasticity. So in reality, something can't be elastic and rigid, that's impossible. But with the advancements in polymers, we can go some way to bridge that gap and give both rigidity and elasticity with the bitumen and the ways in which it's modified. So if we look at this, you can see that styrene gives the rigidity and then butadiene gives elasticity. So you're getting that stiffness and that flexibility, which is key when we're looking at schemes such as the A55 and elastic recovery. So just to show this in a bit more detail, you can see here we've got 3 molecule chains that give examples of different different polymers, different polymer chains, and these polymer chains give us the different behaviours that we try and adapt into our asphalts. If we look at the top molecule, that's a very long chain, so that bitumen has been heavily modified, but it's been heavily modified with a bias towards elasticity. This is important for the A55, where we need that elastic property to give us flexibility and elastic recovery when laying over jointed concrete. So you can see there we've got the styrene, which are the circles, and the zigzag bits in the middle is butadiene. So there's a rigidity there for durability, which allows heavy traffic and minimises rutting, but also there's elasticity in there to a greater extent than we would in other polymers, because we need that elastic recovery to help resist against reflective cracking. If you look at the polymer below, just to go through some other ways of modifying and different things we can achieve with modification, this again is a really long chain molecule, so it's heavily modified, but the bias in this case is around stiffness and rigidity. So you can see in this case there's a lot more styrene, which are the circles, and a fewer or less long chains of the elastic properties. So it still has elasticity, but the bias is towards rigidity and stability. So this is a really heavy duty bitumen that we'll perhaps use on a heavy duty surface such as a racetrack or something like that, where you need surface toughness, elasticity and rigidity all in one. And then the one at the bottom is a shorter chain molecule, so that bitumen is only slightly modified, where perhaps you need a little bit of help with modification in a tight junction on a highway application. You know, we've got a bit of modification in there just to help, but it's nowhere near as modified as the ones above. And I suppose another aspect of this is just to realise that a polymer modified bitumen, or PMB, isn't the same. If you put PMB after a material description, you could get various amounts of polymers or very different degrees of polymer modification, or you'd be getting better bang for your buck. You get more money, more from what you pay for, than sometimes you ask for a PMB and you know you're not getting much bang for your buck. Just to go on that point further about polymers doing different things and not getting much for your investment, this is a spider diagram that just sort of demonstrates this in more visual format, and it's just a bit easier to see. So if we start in the middle, that's just a pen grade bitumen, so it's got no modification in there whatsoever. But if we modify it, we can see that there is a polymer bitumen, but you know you've paid a lot of money for that polymer bitumen, and in reality it doesn't really extend its performance greatly beyond the pen grade. So if you stipulate a polymer bitumen, you could get that, and that is actually a polymer bitumen, so it fits the specification as per PMB, but in actual fact you're getting very little for it. And this is where we can come along, look at your site individual issues, and then tailor make the asphalt with the bitumen suppliers buying to get the right performance. The next colour that comes up there is a bitumen that's modified even further. So we're getting more modification in there, you're getting more bang for your buck. And as you can see in the areas highlighted in red, which are key for the A55, we're getting towards the enhancement areas that we're looking for when overlaying jointed concrete on a major trunk road. So the durability aspects increased, the heavy dynamic loads ability to resist that has increased, and also that resistance to reflective cracking on jointed concrete, we've enhanced that area performance also. But again, we can take that a step further. So if we look at the bitumen that was actually selected for the A55, this is a really heavily modified binder, like we said with the long chain molecule on the previous slide, with a bias towards elastic recovery, with those extended elasticity butadiene molecules in there. So when we look at this, we've looked at the key areas of durability, jointed concrete and heavy dynamic loads. We've picked the right bitumen to go into the right mix to give you that performance in a thin layer over jointed concrete. So why are we going to all this expense and all this sort of investment in technology to get the material right? Well, when we lay over jointed concrete, we have to be acutely aware that concrete is a very different material to asphalt, and concrete expands and contracts with thermal properties. So each concrete slab has a joint in between that's got a joint seal in there which allows the slabs to expand and contract under thermal influences. Now this is a bit of an issue when it comes to asphalt with the joint alone, because that joint, even if it didn't move, would reflect up to the surface. So like I say, a joint alone would make reflective cracks a problem, but when you have concrete that expands and contracts thermally, you've actually got movement that plays into this as well. So as the concrete expands and contracts, as well as the joint, we get bottom-up cracking that propagates to the surface. So what we need to do when we look at carriageways that are built with jointed concrete underlying, we have to mitigate the risks of this bottom-up cracking and reflective cracking. And the way we do this is we put what we call a sami material at the interface between the concrete and the asphalt. This sami material is a very fine asphalt with 10% bitumen content, and this bitumen is the heavily modified binder with the elastic recovery properties that we spoke about earlier. This allows the concrete to move in the way that it moves, and it allows the asphalt also to move in the way that that moves, and it allows the two parts to move independently of each other and not actually create any cracking, and it mitigates that risk of reflective cracking. It's basically like putting rubber suspension in the middle of the pavement layer. But also we have to take into account the fact that when cars, lorries, whatever, drive over these joints, these jointed concrete sections, the slabs actually move under traffic loading, a bit like piano keys. If you run your finger across a set of piano keys, that's basically what the concrete slabs are doing under traffic. Not to the same degree, but you know, you get the picture. So what we have to do again is look at this and mitigate the risks of this cracking from traffic movement. So again, by utilising the same sami material in the multilayer surface course with the polymer modified bitumen in there, this allows the traffic movement to be taken account of, and we mitigate the risks of cracks forming from the top down. So the traffic movement would actually crack the asphalt from the top and propagate a crack downwards, whereas reflective cracking comes upwards from the joint. By utilising these two materials, we mitigate the risks as far as possible in a thin layer. Just to show what we're actually overlaying, this is what we see, and you can see the picture on the left. It is the joint within the concrete slab, and that sort of shows to me that joint needs treating. And the key to everything is getting your substrate as best you can to lay your asphalt. You're only ever as good as what you lay on. So in this instance, we will blast out the joint, we'd clean it, dry it and reseal it. We'd also reseat any slabs that are moving or repair any slabs that are cracked. On the A55, previous to going in and laying any asphalt, there's an extensive survey of all the slabs, and any slabs that were beyond repair were replaced or repaired with a very durable repair and a new joint put in there, so that we're giving it the best chance ever. And the amazing thing with the sami layer, not only is it super flexible, it's very good at waterproofing. So by putting that sami layer in there, you've also got an added waterproofing benefit there. But I can't stress it enough that it is really key that you get the slabs that are receiving the asphalt to the best condition possible to end up with the most durable solution. You can see the sami material on the right there is very rich due to its high binder content, and that's the bit that gives us that rubber elastic recovery property right in the middle of the mat to allow both parts of the pavement to move independently and mitigate that cracking risk. So just to recap, the A55 was a challenging scheme with various thicknesses, not a great deal of thickness to lay asphalt when you're going over jointed concrete. But you know, we worked closely with Manutra, close with the bitumen suppliers to come up with a solution and a material that would best suit those conditions and give the most durable outcome. So obviously the result was that we used multilayer sami. It's been developed over a number of years with various trials up and down the UK, which shows that it's got a proven record of resisting cracking. You know, we've got sections that have got control sections with no mitigation against crack propagation, with geogrids and also with the sami material for comparison. And you know, it's proven to be working out there in situ, and there's been many schemes from that initial trial that we've done using multilayer sami with an multilayer surface course on top. as I touched on earlier, because it is really rich and really fine material, it's got very low in situ voids, so it helps seal the pavement, and that's why it's key we get the concrete slab in the best possible condition before we overlay and get the joints treated and new seal put in at the expansion joints to allow us to waterproof it and get the durability. Again, we talk about sami. Whenever we use sami, we try and use it in conjunction with our multilayer material, so we get this polymer bitumen throughout the construction and give you best chance to the most durable solution possible. It doesn't necessarily always have to be used with a multi-layer surface course. We can put a sami underneath and use a 942 material, we can put a hot roll over there. But like I say, generally in this circumstance, and in particular A55, where we've got extreme sort of issues with thickness limitations, the traffic and the state of the jointed concrete, then this was the only solution available. The way in which we get this high performance is to get the sami material in use with multilayer and get that polymer, that elastic recovery property throughout the whole asphalt overlay.
It's a very interesting question. There's an obvious answer, which is multiplex and averaging beams, but it would always depend on the client's specific needs. What we would always ask is to understand what they want to achieve, and then give them the best possible result and let the individual client weigh up exactly what technologies they feel would be a benefit to the particular scheme.
I think the same can be said for the material selection as well, that there's not always a one fit answer for material. Most people just say put a polymer in there, and yeah, that probably is an answer, but like we've seen on the slides, a polymer's not just a polymer bitumen. There's various others that are out there to manufacture asphalts to the right characteristics for the scheme. So it very much is very specific to the requirements of the scheme and what the outcomes are for the client. I think the key thing is that early engagement with Tarmac. You know, there's a lot of technology we can employ and use if we've got the time to be out there with the client, understanding their needs. So just that early involvement, we can get the technologies sorted out. Any specialist kit that needs to arrive into the site, we can get that planned with plenty of time, and we can employ all the expertise within Tarmac, whether it be traffic management, our technical guys in materials, technical guys in contracting, and obviously our ops specialists like Matt and the rest of his team.
We've got a very interesting scheme, well, a number of schemes coming up, but a really interesting scheme for us. We're currently, as Tarmac, undertaking a maintenance contract in Telford and Wrekin, and they've got a problem in Ironbridge on the wharfage, where the flood defences, when they're deployed, are failing because the road is not smooth enough, and the weight of the water is getting underneath the barriers and making them move and slide across the carriageway. So we've been employed to lay a super smooth to profile road for them that will enable the barrier to sit on a perfectly not flat but equal slope road to enable it to get the purchase it requires to prevent it sliding. That's we're utilising averaging beams and machine control on that scheme, as well as multiplex. So again, it's cherry picking which ones of the technologies we need to use out of the 6 for each specific scheme we're challenged with.